Now let's talk about how to calculate the p-value. Okay, so we know that hypothesis test allows us to find a probability that a particular value can be observed, assuming that null hypothesis is true. Meaning, for example, for the average value, it gives us a chance to get a sample with this average, or even more extreme, it means it will be even more far from our null hypothesis, the true population average we believe in, assuming that our null hypothesis is correct. Okay, so this probability is called a p-value, and let's learn how to calculate it. Well, so the idea is following. We need, for a given sample size, we need to find a probability. Let's say if we take another sample of the same size, how likely it will be at least that far as ours, or even more far. Okay, so it means it's even more extreme. Now let's get back to our example with height values. Okay, let's say this is our sample. I'll remind you that our null hypothesis here is that the mu is 170. So that's the average height of all adult males in Alberta is 175. Okay, so we got a sample of size 16, and this is the t-value. Okay, this is the t-value. So it means that our sample is by one standard error is larger, or average of our sample is by one standard error is larger than average of the population we assume about, right? So this is the measure of extremeness, one standard error, okay? And our idea is, if we repeat this experiment, how likely our new sample will be that extreme. So it means that it will also be far from the population average by one standard error, or even more. It means 2 and 3 and so on. Okay, so 1 is a measure of extremeness in this case. Now look, first of all, if we take a sample with -1, it will be the same, right? The extremeness will be the same, because it will also be one standard error far from the average. In our case, in this null hypothesis, when we compare it with equality, the negative and positive t-values will be equally extreme, right? So if you have a sample that is by one standard error larger, the average by one standard error larger than average of population, and by one standard error smaller than the average population, they are equally extreme, okay? And then what's the probability to get a sample that is as extreme as ours? This is as extreme as ours, standard error, or more, okay? So these are all these samples. It can be 1.1, 1.2, 1.5, 2, 3, and so on and so forth. So all these samples are more extreme than ours, okay? And also all these samples are more extreme than ours, right? So what's the probability to get one of these samples here? Well, of course, it's this area, okay? So the area under this distribution curve will give us a probability to get a sample that is as extreme as ours, or even more extreme, okay? So we can calculate this, the area, this one and this one. So P1, it's a chance to get a sample which will have average by one standard error larger or more. And P2, it's a probability to get a sample that will have an average by one standard error smaller. Okay? And then the sum of these two will give us a p-value. So it's a chance to get a sample which is as extreme as ours, or even more extreme. How to get a P1 and P2? Well, if we know a distribution, if we know a value, in this case a t-value, then it's a CDF function that gives us a probability. But you remember, the CDF function gives us always a probability to get equal or smaller value, right? So it means that P2, that's the simplest one in this case, P2 will be the CDF function for -1, it's a t-value, right? And then the n-1 degrees of freedom, okay? What about P1? Well, P1, it's on the right part, so we need to find, the CDF always gives us a probability on the left part, right? So it means it will be 1 minus f of t-value equal to 1, and then n-1 degrees of freedom, okay? So you remember that in R, the CDF is always a p function, so it means that you can use this code in R to find the probabilities. So it will be pt minus 1. In this case, we have 16 values in sample, so it will be 15 degrees of freedom. And then P1, 1 minus PT, 1 and 15 degrees of freedom. But actually, it can make your life a bit easier because apparently this distribution is symmetric. So P1 will be equal to P2. So you can find one of these. For example, you can find the P2 or P1 and then just double it, which will give you the value you are looking. Now, let me show you the example with the 3 samples we have discussed before when we talked about rejection regions. Now we can calculate the probability. Okay, so let's start the first sample, 174. Is average 174, where we have t-value is minus 0.5. It means that it's half of standard error smaller than our population average we assume, right? So this is how it looks like. So we have 0.5 here, we have minus 0.5 here. So both values will be equally extreme, right? So it's by 0.5 far from the real population average. And then all these samples with t-values above 0.5 or below minus 0.5 will be even more extreme, right? So it means that that's the probability. So you just take this area and this area and sum up. Okay. In our case, it will be each area is 0.3, and then the p-value will be 0.624. So it means that assuming that our null hypothesis is true, 62.4% chance that if we repeat our experiment, the sample will be as extreme as ours or even more extreme. Okay, so it means that our sample is actually not that extreme for this null hypothesis. And because it seems that null hypothesis is something that we expected most, then we can't reject it. The sample is pretty okay for the null hypothesis, right? So let's look at the second sample. Here we have a little bit more extreme case. So the t-value is 1. And again, we use the same idea. So that's the sample that is as extreme as ours. And this sample is also as extreme as ours. It's by 1 standard error, larger or smaller than the population average we assume. And then that's the area for getting the probability. This area gives us a probability to get a sample as extreme as this one or even more, or this area is a sample as extreme as this one. And then we can calculate the p-values. You can see that the p-values in this case smaller because we have a more extreme sample, and then the resulting p-value is 0.33, which is still pretty large. So if we repeat this experiment, 33.3% chance to get a sample as extreme as ours, or even more extreme if the null hypothesis is correct. So it's pretty likely. So we can't say anything wrong about this. Okay, it's likely to get a sample like we have. But if we take the third sample, then we have t-value minus 3, right? So this is how it looks like. So this is minus 3. Here we have minus 3, and here we have minus 3. So the area, the chance to get a sample even more extreme is this one, right? And then we have this one. Okay. Then if you calculate the p-value, you can see that it's very small. It's less than 1% chance to get a sample like we have, or even worse if we repeat this experiment, assuming that null hypothesis is correct. So it seems that this sample is too extreme for this null hypothesis. So it seems like our assumption about the population is not correct. So in this case, we reject null hypothesis based on the information about it. So that's the basic idea. And I must say that when you look at the p-values, it's very common to compare it with what is called significance level. Okay, you remember already that significance level is something opposite to the confidence level, right? For example, if confidence level is expressed in percent, significance level, it's the opposite value, but not in percent. It's a ratio of 1, right? 0.05. So it means that 5% out of this, right? So 99% of most common values, and then it means that 1% of the values is extreme. So this is alpha, this is significance level. And in many statistical books and in many journals, you will find out that people compare the p-value with a significance level. And then if p-value is smaller than the significance level, they reject null hypothesis. If p-value is larger, they accept it. Well, it's not a very good, actually, way to do that. Always think, accepting or rejecting null hypothesis, it's your decision, okay? You take the risks. P-value gives you this risk. And therefore, you should think about risks, not about these fixed limits, but you can estimate the risks. What happens if you reject or accept null hypothesis? We will discuss a little bit more about these risks in this lecture. Okay, so that's the typical algorithm for the t-test. So you calculate the t-value, then you calculate the p-value, then you compare it with significance level, right? Then if it's below significance level, you reject null hypothesis. If it's above, you accept null hypothesis. Okay, but once again, don't use it. don't use it this way. Always look at the p-value and try to estimate the risks of accepting or rejecting. And it's very important that p-value should be always supplemented with the confidence interval. We will discuss more details later in this video. And let me show you why it's not very good idea to compare p-value with a fixed. Okay, that's one of the nice comics I got from XKCD. And look, very often the confidence limit or the significance level is 0.05. Okay, so it gives you 5% chance that your sample still came from this population, but you will reject null hypothesis. So what if you get a p-value 0.499999? If you use this rule, you will reject null hypothesis because it's below 0.5, right? But what if you get a p-value 0.5? Well, in this case, it's equal to 0.5. So you will accept null hypothesis. But look, what's the difference between these two values? It's nothing, okay? So that's why it's not very good idea to compare one of the reasons, actually, not a good idea to compare your p-values with some fixed threshold. Use p-value to make a decision, and then explain why you make this decision and explain the risks that this decision will take.